15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on Space Nuts, where we talk astronomy, space science, and all sorts of other weird and wonderful stuff, and answer audience questions from time to time as well, as you would have heard last week. In today's program, we've got some really interesting stuff to talk about. Scientists may have found a solution that explains where some of Earth's water comes from. Fred and I have talked about this before, that it didn't add up. We've got too much water, so where could it have come from? Well, it looks like our sun may be responsible. That's my wife and I's son. He's 32 years old. No, the one out, there, 8 minutes away as the crow flies. So how could that happen? We'll try and figure that out. And there's been some new data that reveals that most of the dwarf galaxies in our part of the universe are relatively new, and some of them are known as satellite galaxies because they're orbiting our galaxy, but some of them just wave as they go past. It's really fascinating. So we'll look into that. And a couple of audience questions, one about the radiation of gas giants. And this is a really good question. It's a black hole question, surprisingly. But they're asking, how can a star become a black hole if it loses mass? Wouldn't it, lose all its energy, and therefore how could it become a black hole which has got so much energy? Good question. We will tackle all of that today. I am your host, Andrew Dunkley. Joining me, as always, is astronomer at large, Fred Watson. Hello, Fred.
Hello, Andrew. How are you doing?
I'm all right. I'm sick of being wet. It's been raining here for...
You are, yeah. We're a bit tired of it down here in Sydney as well. Yeah.
Good grief.
But, yes, at least living on the side of a hill like we do, we're not flooded, unlike many people that I know between here and you, in fact. There's a lot of flooding.
Well, we've got flooding to our south, flooding to our west, flooding to our north. So far, so good for us. But our river did rise last weekend to a precarious height. We're lucky enough to have a massive dam upstream of us, which holds 3 to 5 times the volume of Sydney Harbour. And it's at 141% of capacity at the moment. And people go, how is that possible? Well, it's got about a 50% flood mitigation level. So when it's at 100%, you can fill it up half as much again. It's a remarkable dam. So it
must be Burrendong.
Yeah, Burrendong Dam. It's holding back a hell of a lot of water at the moment. So if we get any more rain, things might change around here, but we're just keeping our fingers crossed. I feel sorry for the farmers because they were about to harvest and the rains come at the worst possible time, and that follows a mouse plague and a drought. I mean, seriously, They just can't take a trick. I wouldn't be a farmer for quids. In fact, there's no money in it at the moment, so very, very difficult times.
Yeah,
it is. It is a tough gig. All right, Fred, to our first story, and scientists might have found a possible solution as to how the Earth has as much water as it has. And up until now, we've thought, okay, when the Earth was being formed, it was just a dirty old dried up pile of rock, and then a few asteroids and comets hit it that were made of ice, and they left their water here, and yay. But it didn't add up, never added up.
It didn't add up, that's right. And there's also other things that you and I have spoken about, actually sometimes in great detail, that don't add up, about the isotope ratio of the water, whether, the extent, it's this mixture between what you might call light water, which is normal H2O, and heavy water, where the H is replaced by heavy hydrogen, which is deuterium. And the ratio of light to heavy water is a kind of signature of where that water has come from. And so the idea that all the water in the Earth's oceans had come from comets took a bit of a knock when the comets whose water content has been analysed turned out to have the wrong isotope ratio. One or two comets do have the right isotope ratio. In other words, one's one that matches the water in the Earth's oceans, but some of them don't. Some of them are quite different, and in fact, most are quite different. And that's this isotope ratio is something that is. So it doesn't change very much. I think it changes a bit, but not much. So if you've got the wrong kind of water making the oceans, then you clearly got something wrong. It's not that's not where the water came from. And I think that I seem to remember that led you and I into long discourses about whether you could drink heavy water without becoming radioactive and all kinds of things like that.
I think we
won't do that.
We even went as far as talking about, what if you came across a planet that was primarily made of heavy water? Could you live there? And the answer was basically no. We couldn't do it.
Yeah, that's right. So I think, if I remember rightly from those discussions, you could probably get away with a glass or two of heavy water, but if you tried to live on it, you'd basically fall to bits in a medical sense rather than physical. So all that notwithstanding, that's just it's just to illustrate that there are problems with our understanding of where the Earth's oceans came from. So another theory that was put forward to counteract the problem with the wrong kind of water coming from comets is that the water content of the Earth was always there, bound up in the rocks of the Earth. That when the protoplanetary disk was being formed around the sun, in which the planets basically grew by accretion. Those grains of dust and things of that sort had water bound in them, which then became part of the rocks of the Earth. And in some way, that water disassociated itself from the kind of chemical or molecular binding and ended up in the oceans. But that's another theory that I think has problems.
It doesn't hold water?
I wish I could admit to having set that one up for you, Andrew, but sadly, I'm just not that clever.
I don't think it was very clever.
Let me think of another
I can hear
one.
The groan.
Wait a minute. Here's one. I think that other theory might have gone down the drain. How's that? Yeah, it's the best I can do.
Dear, oh dear.
All right. Yeah. So, but the problem is you've still got a deficit. Exactly as you said, you've still got a deficit of water. We don't know where most of the water in the Earth's oceans came from. There seems to be too much of it here. And the same could be said, of course, of the planet Mars, because Mars originally we know had huge reserves of water, much of which is still there as ice. So the same question would arise: where does this stuff come from? So some new work which has come from analysis of grains of dust from the Japanese Hayabusa mission, which you might remember there have been two Hayabusa missions, Hayabusa and Hayabusa 2, both of which returned samples of asteroid material back to Earth. The second one returned samples of an asteroid called Ryugu, and those I think are still being analysed. But the first one, which I think it returned in 2010, this was the original Hayabusa, actually visited an asteroid called Itokawa and took samples from that, and then had a devil of a job getting back to Earth, though everything went wrong. And I think it had to do a flyby of Venus, or it was astonishing the way the
like an extra several years or something.
Yes, yeah, that's right. It did. The JAXA, Japanese Aerospace Exploration Agency, they deserve enormous credit for rescuing that sample, because I can't remember what happened. I think the Iron rocket failed or something like that. So it wound up in an orbit that was not where it was meant to go to intersect the orbit of the Earth. But by waiting a while, they found they could get a slingshot from Venus, and there was enough power in the thrusters to try and change its attitude and things. And eventually it got back to Earth. It is an astonishing story. Yeah. So, but we're not talking about that extraordinary interplanetary peregrination. We're talking about the results that came from it. And some of those samples from asteroid Itokawa wound up at the University of Queensland here in Australia, where they've been analysed by a group led, I think, by planetary scientist Professor Trevor Ireland, who's basically, his skills are all in the dust particles that make up planets and asteroids and things of that sort. And what they've discovered is that the surface of dust grains from the asteroid Itokawa, they are rich in water. Basically, it's probably ice, I think, but it's water, and it's the surface that's rich, and that's a kind of hint that what you're seeing is the effect of dust grains that are being fed by water. And the bottom line that these scientists are, or the conclusion that these scientists are drawing, for good reasons, is that it actually is water, wait for it, Andrew, from the sun, which doesn't sound all that sensible. No. But of course, the sun spits out protons, which are hydrogen nuclei, and electrons. And that's the kind of the raw material that, from the solar wind is the raw material of hydrogen. And once that solar wind deposits itself on cold surfaces like the surface of an asteroid, then you get basically hydrogen and deuterium appearing on the surface of those dust grains. And it's a fairly complex chemistry, which amounts to the impacting hydrogen essentially tears apart the silicon and oxygen. So that's the silicate, SiO2, which is what makes rock, is a silicon atom and a couple of oxygen atoms. And you basically, if you prang it with a hydrogen atom, or a hydrogen nucleus going at high speed from the sun, it breaks the bond between the silicon and oxygen, and you then get a reaction taking place, which makes both what's called a hydroxyl radical, that's OH, oxygen and hydrogen, one atom of each bound together, and the more common water molecule, H2O, with two hydrogen atoms bound to one oxygen atom. And so what it's saying is that this curious mixture of the solar wind and a bit of surface chemistry means that you've got a potentially rich reservoir of water on the surface of dust grains of objects in space. And that doesn't just mean asteroids in today's solar system. It means the moon over the history of the solar system, and the Earth in the early history of the solar system. So they're suggesting that basically there is an untapped, there you go, there's another
unaccounted
one,
for.
Source. Yeah, all right, unaccounted for. No, I was going to put it the other way, an untapped idea or theory in the origin of water, that it may well have come from the solar wind.
So this would have been as the planet was forming with the big...
I guess so, although, reading the scientific literature on this, it sounds as though this process is going on today, because Trevor Ireland, who I just mentioned, there's some nice quotes from him I think this is a nice quote. The ability to trace water in the crust of a speck of dust is really neat, he describes it as. I beg your pardon, Trevor Ireland wasn't involved with this study. He's commenting on it. I do apologise. Let me just get this straight then, because I've actually downtrodden the real authors of this work. This is terrible. One of the authors is actually Steve Reddy, who's at Curtin University. I had it in my mind that it was Curtin University, and then saw Trevor Ireland's comment, but he's actually not involved with this study, but he's a fan of it. Let me put it that way. So Professor Steve ready is at Curtin. He is one of the authors of this work. If he's listening, I do apologise for mangling this account of his studies, but it's the comment that comes from Trevor Ireland, which is basically to the effect that it's really neat that you can actually the top 50 nanometers of the surface of a dust grain, and 50 nanometers is something like probably a tenth of the wavelength of light. That puts it perhaps the best way. It's a very small amount. It's a tiny, tiny distance, but you can actually look at that top 50 nanometers of these dust grains and establish that there's water. And he says, this is again Trevor Ireland, he says the potential of the solar wind to generate water had important implications for establishing a base on the moon. If you can establish, he says, that there is actually water being generated in the lunar soil by proton bombardment by solar wind, then that gives a potential resource in the future for water supply.
I was going to ask you if they think this is something that continues to happen, and it sounds like it does.
It does.
And when you consider the size of the Earth, and it's been basically created by lots and lots and lots and lots of grains of dust, that's a lot of water coming together.
It is. That's right. They're essentially. I guess just scratching the surface. There's no pun there, I don't think, but scratching the surface of this idea that the solar wind, these hydrogen nuclei bombarding the Earth all the time, might well have contributed a significant fraction of the Earth's water. I don't think they're ruling out that maybe some of it came from asteroids and comets. Some of it might have been within the rocks of the Earth all the time. But this has just opened up a new mechanism for providing the Earth's water.
This could account for the differential in what we believe should be the amount of water we have versus what it. The shortfall basically between
what should be there.
Yeah, I like the theory. I do very much like the theory. It's very clever thinking, and not something that would come. You got to wonder how someone came up with the idea. I suppose the evidence was in that sample they got.
It's in the samples.
Okay. So, here we go.
Here we go. New idea. Bing.
There might be more to this too. So I guess they'll be investigating further, and we might be able to confirm one way or the other whether or not it does in fact hold the answer to the mystery of how much water is on Earth. It also prompts me to wonder about the ice moons. Would they have developed the same way, or is that a different kettle of fish?
No, that was the thought in my mind as well. And, bearing in mind that the ice moons actually contain a lot more water than the Earth does. I think Europa, has twice as much water as in all the oceans of the Earth. It's yes, maybe this mechanism works for them as well. Whether you can extend it to that, I don't know. But I'm sure these authors have thought of that, and maybe that'll be the next paper that they...
Yeah, lots more to learn. Got another theory for you, Fred.
Oh,
it's a water theory. I've been trying to find a good place to use this piece of information that I came across, and this seems like the perfect opportunity, seeing we're talking about water. So the Earth's 70%, 71% covered in water, correct?
Indeed.
It's uncarbonated, correct?
Indeed.
Yeah. Well, that proves the Earth is flat.
Because
it's uncarbonated.
It's uncarbonated. Da-da! Oh, gosh. So that's one of yours.
No, I read it somewhere. I've stolen that one.
I do like it. I do like it.
So the flat earthers are right. The Earth is flat because the water's uncarbonated.
Yeah.
All right, that's enough dad jokes.
I think that was a granddad joke.
Probably was. Actually. Oh, well, actually, that gives me that dovetails beautifully.
Oh, yes. It does, doesn't it?
Grandchild number 4 arrived on Sunday.
That means
Felicity Ellen is her name, so we welcome her to the
lovely.
world.
That's lovely. What a lovely
I'm
name.
not going to tell her the truth
Congratulations.
about the world as yet because she's too young to understand, but hopefully it'll be better when she comes of age because it's not very happy at the moment.
Well, the best thing you need to tell her is that she's a Dunkley.
Yes, she is. Yes.
That's.
I think I mentioned once before that when our first granddaughter was born, she was the first Dunkley girl in 50 years. Well, now there are 3.
Yes. Oh, that's astonishing. Well,
poor Nathaniel.
You've done the poor Nathaniel. You've done the Dunkleys proud, if I may say so.
All right, moving on. This is Space Nuts with Andrew Dunkley and Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, I've mentioned social media many times because we are on all sorts of social media platforms these days. We're on Facebook, where we've got our official Facebook page. We also have the Space Nuts podcast group, which was created by the audience, where you can talk to each other. We are now on Instagram. So look for spacenuts.io if you want to follow us on Instagram. Got a nice note the other day from someone said, "You're finally here. I can follow you. Yay." And we're on YouTube, where you can catch video editions of Space Nuts. So all you have to do is go to spacenuts.com/c/spacenuts, and there we are. And you can subscribe to Space Nuts through YouTube as well. Now, Fred, this is some new data that's looking at dwarf galaxies. Now, there's lots of dwarf galaxies sort of surrounding our galaxy. Some of which we've already eaten, some we're leaving till later. Some are referred to as satellite galaxies because they are actually in orbit around us, but some are not, and they just sort of go, "See ya," as they pass by. Now, this has all come out of some new data, which was revealed by Gaia. So what are they actually trying to tell us they've discovered?
I think a really quite significant discovery about our galaxy. So just reminding us what Gaia is, it's a spacecraft which is measuring the positions of stars with incredible accuracy. And by position, I don't mean three-dimensional position in space. I mean its direction in the sky. That is the science usually known as astrometry, measurement of the position of things regarding the sky as though it was just the inside of a sphere. But that's very important because if you can do it with the sort of accuracy that Gaia is doing, then you can spot the motion of objects. Stars move relatively slowly, and certainly when I was a young astronomer, there was only about one star that really moved perceptibly within 10 years. And now Gaia can measure their position so accurately that you can look at them over a baseline of just 3 or 4 years, or even less, and still get very accurate measurements of the velocity of stars across the line of sight. And so what's happened is that not only has Gaia been looking at the stars in our own galaxy, it's also been looking at dwarf galaxies, of which there are many. I've forgotten the number. I think I mentioned it in Spacewalk, but I can't remember what it is. It's tens of dwarf galaxies, might be 60 or something like that, in orbit around. Sorry, not in orbit, but around our own galaxy. And the normal view is that all of these objects were formed round about the same time as our galaxy as offshoots. And indeed, it's true when you look at simulations of galaxy formation, and some of the modern simulations are extraordinarily accurate. What you get is you can generate a spinning disk of stars and gas and dust like the real thing, but you also get all these satellite galaxies being formed, often many hundreds, in fact, in the simulations. So what has always, or has generally been assumed, and I have to say, Andrew, it's only in my lifetime as a working astronomer that most of these have been discovered. I think Sagittarius dwarf was one of the first discovered, and it was discovered at the telescope I worked at for many years. So they're relatively new features as we've got bigger and better telescopes and been able to see these faint aggregations of stars which represent dwarf galaxies. So as I said, there are many of them known, and the assumption has always been that they're all gravitationally bound to our own galaxy, the Milky Way galaxy, which means that they are in orbit around it. Now, the Gaia data has revealed that for many of these dwarf galaxies, that's not correct because they're going too fast. A little bit like, you remember your old friend Oumuamua, as it careered through the inner solar system. How did we know it was an extra solar or an interstellar asteroid? How did we know that? Because of its speed. It was whizzing through the solar system too fast to be grabbed by the sun. It had come from somewhere else. And a similar thing has been discovered in respect to these dwarf galaxies. It's basically work led from l'Observatoire de Paris and other Parisian institutions with, I think, a largely European list of authors, which you can't find at the moment, but never mind. It's a remarkable discovery, and it's fairly close to home. Some of the work I've been involved with over the years, including projects which I'm still peripherally involved with, although I haven't done much for quite a while, called GALAR, which is Galactic Archaeology with Hermes. Hermes is an instrument. Those projects are looking in detail at the chemical and dynamical, in other words, the way it moves, dynamical structure of our galaxy. And so this work on the dwarf galaxies is very much part and parcel of what that's all about. So what it looks like is that we are seeing a situation where you've got the Milky Way, a massive spiral galaxy, which does have objects in orbit around it, which generally speaking are being torn to pieces because of the tidal effect of this giant galaxy right next door. It just tends to, a bit like the tides are raised on the Earth by the moon, tides are raised in galaxies by dwarf galaxies by a large mass like the Milky Way. It pulls one end harder than the other, and so you get essentially this. You get this horrible tidal distortion, it's called. So the Sagittarius dwarf galaxy I just mentioned, that's being pulled to bits in this way. But some of these are not having that effect because their velocity is too high for them to be in orbit. They might, the Milky Way's gravity will be grabbing them as they go past. But the bottom line is that unlike the traditional view, these objects have not been in orbit for many billions of years and are circling the Milky Way for the first time. It's really quite astonishing, in fact, that this is it's such a change in mindset, to put it that way, that it's really quite a remarkable discovery.
Yeah. So if they're moving too fast for us to actually catch them, and some of the ones we have caught have already been absorbed into our galaxy and are being redistributed, I think was the word I read. Yes. What will happen to these ones if they're passers by? They'll just sort of meander off into another part of the universe.
Yes, actually, more especially, they'll still be part of what we call the local group of galaxies, which is about, a couple of dozen galaxies, three big ones, ourselves, the Milky Way, M31, the Andromeda Galaxy, and the other one in Triangulum, whose number I've forgotten at the moment. It'll come to me. Never mind. There are these three big spiral galaxies, and so that they're the nucleus of the local group. And it's likely that these dwarf galaxies certainly belong to the local group, but not necessarily bound to our own galaxy.
Okay. So could they get sort of snaffled by one of the other two?
Yeah, maybe so. Yeah, if they go in the right direction for a few billion years, maybe they will. M33 is the other galaxy I was thinking.
There you go. Of course, that's going to prompt questions because we know that in the distant future that Andromeda and the Milky Way will combine. So if there are these other dwarf galaxies sort of speeding past us saying, ha, you can't catch me, but Andromeda does catch it, does that mean we end up getting them anyway?
Maybe so, that's right. So the combined galaxy from the collision of the Milky Way and Andromeda is usually called Milkomeda. It will be a. I mean, we're talking now not trillions, but many billions of years into the future. It will be essentially an elliptical galaxy, because the gas content of the two spiral galaxies will have been used up in star formation. And it seems likely that these dwarf galaxies, they will be collateral in the collision. They'll probably catch a knock from this gravitational disruption of the Milky Way and Andromeda, and wind up as probably well-behaved stars in the but ancient stars in the Milkomeda galaxy.
Milkomeda, I like that. I haven't heard that before. And that'll all happen in super slow motion, won't it?
Yes, it does. Yeah, so slow that if you're on a planet or in orbit around one of the stars of one of these galaxies, you probably won't notice it.
No. You have to live to a very ripe old age to witness it, I think.
Yeah. Couple of billion years
indeed.
To do it.
All right, interesting stuff. This is the Space Nuts podcast. My name is Andrew Dunkley, and he's Fred Watson.
Space Nuts.
Now, I've mentioned our patrons a few times, and it's really great to be able to welcome new patrons on board. We've had quite a few sign up in recent times, so we appreciate that, putting a few dollars in the can for us every month to help fund Space Nuts. We appreciate it. If you would like to become a patron, all the details are on our website, spacenuts.io or spacenutspodcast.com. Just go on the supporter link and find out what you can do there if you'd like to become a patron. And I've noticed on social media, Fred, that a lot of the patrons are starting to get their presents turn up in the mail. We're not telling them that they're receiving presents. They're just turning up, and they're showing everybody on the Space Nuts Podcast Group Facebook page what they're receiving, and there'll be more to come. So if you sign up as a patron, there are extra benefits, as well as a fully commercial-free version of the podcast and much more. So, have a look into it. If it's not for you, that's fine. There is a 30-day trial, so you can give it a go, and if it's not for you, that's fine. But if you'd like to continue on, that's terrific. Now, Fred, we've got a question here from Fenton, who has come up with one we haven't had to answer before. So this will be refreshing.
Hi, guys. This is Fenton calling you from St. Paul, Minnesota in the U.S. And I have some questions on Jupiter, in particular the radiation that's emitted from it. What's known about that? I understand that it's not a settled question. And then also radiation, does that come from Saturn, Uranus, and Neptune? How much radiation do they give off as well? And in all four cases, how is that going to interfere with the possibility of life on all four planets? Is it going to fry it? How far out will it fry it? Etc. Thanks a lot. Enjoy your show. It's better than the gloomy news that you will hear every day, probably in Australia too. Bye now.
Thank you, Fenton. Yes, there is way too much gloomy news in the world at the moment. I don't disagree with you there. Radiation from the gas giants. He cited Jupiter, but I suppose it can apply to all of them. Where do you want to start on that one?
Well, Jupiter is sorry, Andrew. Jupiter is the most radiation strong planet in the solar system, and I think the other gas giants are a fairly pale shadow of Jupiter in that regard. Of course, it is the biggest of the planets. It's got the strongest magnetic field of any of the planets, and that extends out into. It dominates, so the Jupiter's magnetic field dominates in a region which we call the magnetosphere. The Earth has one, Jupiter has one too, but Jupiter's magnetosphere is basically 1 million times bigger than the Earth's in volume. Wow. It's very big indeed. So you've got this large region around a large planet which is dominated by strong magnetic fields. And what that means is that any subatomic particles that wander into that region, and of course the sun's spurting these out all the time, any subatomic particles get accelerated by this magnetic field, and they become radiation because they are high energy particles. Actually, there's another slightly quirky aspect of Jupiter's radiation field, and that is that not all the subatomic particles come from the sun. In fact, most of them come from another source not very far away, which is Jupiter's moon Io, or Io, depending on which way you want to produce it. And the statistics say that every second, a ton of sulfur dioxide gas is squirted into space by the volcanic activity of Io, and basically as soon as that gas gets into space, it turns into sulfur and oxygen, and that is actually that coupled with those ions, which means they've got no electrons. Those ions actually form the radiation material, if you can put it that way, being accelerated by the magnetic field. And actually, there's a really neat effect which has been observed by many spacecraft. There are currents between Io and Jupiter's upper atmosphere, the ionosphere, which amount to 1 million amps. High current on Earth is 10 amps if you've got, a heavy piece of kit, a heater or something like that. These are 1 million amp currents. Of course, they're flowing through what amounts to empty space. But it's those currents, and they're driven by the particles that have been ejected from Io itself. They actually turn into aurorae on the planet itself. It's how we see the aurorae of Jupiter because of this stream of stuff coming from Io. So it really is, the question is absolutely on the money. That what is the effect of this amazing magnetic field around this giant planet, and it's pretty devastating because the radiation belt really acts exactly as the word suggests. It's a belt of these high fluxes of particles, probably in the shape of a donut around Jupiter's equator. It makes me think of images. I used to, when I was doing talks about why we have different sorts of telescopes in the astronomer's arsenal, I used to show 3 pictures of Jupiter. One was the normal one we see with visible light, where you've got the cloud belts and the great red spot all visible in reflected light from the sun. But then if you go to the infrared region of the spectrum, you see Jupiter's cloud belts, but what they're doing is the cloud belts are dark and the space between them is bright, and that's because you're seeing the heat of the planet leaking out between the cloud belts, the infrared radiation. But then when you go to the radio spectrum and look at what Jupiter appears in a radio telescope, it's basically got these, it's a disk, a rather ill-defined disk, but with these 2 brilliant, what you might almost looking like ears to one side and the other, which are this donut shaped, you're seeing edge on this donut shaped radiation belt, because the radiation belts are extremely prominent in the radio region of the spectrum. So we know all that. That's telling us that yes, these radiation belts are very strong. What will be the effect on life? You don't even need to look at life to see its effects, because if you put a spacecraft in orbit around Jupiter too close in, all its electronics get fried because of the intensity of the radiation. And that's why the Juno spacecraft is in a very elongated orbit. So it spends most of its time outside the radiation belts and just plunges inside them for a brief period on each of its orbits. I think the answer to the main question there, what would it do to life? I think it's pretty grim in its effect on life. I think that we're likely to be looking at an environment that would really be so damaging to any kind of microscopic organisms, let alone higher orders of life, that you really will be in trouble. Having said that, Europa, which is outside the radiation belts but not too far away, is still considered to be one of the top candidates for the possibility of finding life within the solar system. The oceans of Europa underneath the ice, the ice caps, which themselves would give, the ice crust of Europa, which would give a little bit of protection from the radiation field, but not that much.
As Jupiter orbits the Sun and interacts with Io as it does, we think about the radiation being around and emitting from the planet. Does it leave a trail of radiation as it goes, or does that dissipate, or what happens to it?
I think that's a really good question. And I'm not enough of a particle physicist to know what the answer is. But I think what's happening, subatomic particles must leak from the Jupiter's magnetosphere. And my guess is that they are going at such high velocities that they will just, they won't be particularly take much notice of Jupiter's orbit. They'll just spurt out into space, I think. My guess is they will become effectively part of the solar wind, blowing perhaps stronger in one direction than the other. But it's a really good question. I don't know the answer to that, Andrew.
I stumped Fred.
You need a badge.
Should be a badge, yeah. Fenton, thanks for your question. Hopefully we gave you an adequate answer, which is what we strive to do here on Space Nuts.
Yeah.
Now we're going
Never a
over
good one, just adequate. Never a good one, just adequate.
Yeah, that's right. Now we're heading over to the UK, Maidstone, Kent, where Gareth resides. He says, I'm puzzled about the formation of stellar mass black holes. Yes, yet another black hole question. It's okay, Gareth. It's all right. Don't lose any sleep over it. Assuming gravity is proportional to mass and light can escape from any star, otherwise we wouldn't see them, then no star that we can see has the mass to trap light as a black hole does. If most stars lose mass rather than gain it at the end of their life, how can any visible star ever become a black hole without accreting significant mass at some point? What am I missing? Thanks for the great and informative podcast. Ooh, that's a good question.
Yes, it is a good one. And I guess, what we should do is look at how a stellar mass black hole is formed from the collapse of a star. We think some of them are formed that way. If you've got a star whose mass is about 20 times the mass of the sun, it's shining away. Most of the radiation that we see comes from its outer envelope, which is it's the part where the nuclear processes are not taking place. They're taking place in the core, which is the very center of the star. But that heats the envelope around it, what you might call the atmosphere of the star. And that's the source of the radiation that we see, the light that we see. Now, what stops the star collapsing at that point is the outward pressure of that radiation. It's what's stopping the core collapsing. So a 20 solar mass star will, we think, eventually explode as a supernova. And the outer envelope is blasted off to make something which we've known and studied well, clouds of gas known as supernova remnants. There are many of them around our galaxy. Famous ones include the Veil Nebula. There is, what's it called? There's a very prominent one here in the south. And I can't remember what constellation it's in, but, it's a remnant of a supernova. Now, the core itself, though, when the hydrogen burning stops, so you don't have the outward radiation pressure, that core collapses. And if the core is more than about 2.2 times the mass of the sun, it will collapse to a black hole. Less than that, and it'll collapse to a neutron star. But more than that, it'll collapse to a black hole. Nothing will stop the collapse, and it turns into a singularity. And the key thing about the singularity is that yes, it's got say, 2 times the mass of the sun, but it's not a 2 solar mass star. So the bit of it that released the light out is long gone, and what you're really seeing. This is another difference between a 2 solar mass star and a 2 solar mass black hole. The black hole has got this incredible gravity well. It's like, if you imagine gravity as a surface, it disappears down a plug hole. Basically, it's an incredibly steep gravity well, and it's that stops the light escape. Whereas light can escape from a 2 solar mass star with no problem, but from a 2 solar mass black hole it can't.
Okay. So, just to clarify it in my mind, it's a much, much bigger star that becomes a 2 solar mass black hole.
Yeah.
So,
yeah, because the outer layers disappear off in the explosion, and the core itself is the bit that becomes the black hole.
Okay. All right. Makes sense. So it is big enough to become a black hole. It's just it doesn't become the same size black hole as it was.
Yes, that's right. So the star, the black hole is less than the mass of the star because half the star has been blown away. But the key thing is, and the key reason, I think the heart of this question, it's about the gravity gradient. The black hole is a single point, and that's what stops the light getting out, the event horizon. Okay. Whereas a star's not like that. A star's much more like the Earth.
All right.
It shines in the dark.
There you go. Something to ponder, Gareth. If you were confused then, what are you thinking now?
Yeah, you don't sound convinced, Andrew. I'm not sure I am either. But never mind.
Well, no, I suppose it's just it's sort of the questions we get most often are about black holes or dark matter. Dark matter is fast catching up as the most popular genre when it comes to questions, but black holes still mystify people, and getting your head around something as unusual as that always prompts questions. So that was a good one to ask because we know black holes don't allow light out. So how can a star become a black hole if they can't, don't have the power to stop their light from escaping? It happens later.
It does.
All right. Thank you, Gareth. Thank you, Fenton. Thank you, everybody, for listening. Hope you enjoyed the program. And that wraps up yet another episode, Fred. It's been good fun.
It has been good fun, and we look forward to another one before very long.
Yeah, hopefully they won't ban dad jokes because then I'd have nothing to talk about.
No, you keep up the good work, Grandad.
Yeah, sure. Okay, thanks, Fred. We'll catch you next week.
See you later.
Fred Watson, astronomer at large, part of the team here at Space Nuts, and Hugh in the studio. As always, thank you for your support and help because he does work very hard. He certainly did quite a bit of work on the program for us last week when we ran into some technical snafus that we didn't know had happened until it was too late. It was like a black hole. It just all happened after the event. And from me, Andrew Dunkley, thanks again for your company. Don't forget, if you do want to send us some questions, go to our website and click on the AMA tab or the button on the right-hand side to send us your audio questions. We take text questions as well. Always great to hear from you. Don't forget to tell us who you are and where you're from. Until next time, thanks for joining us, and we'll see you again real soon on another episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.